This discussion is an intro to intermolecular forces. We have already looked at the type of forces that hold atoms together within a molecule, and these we refer to as intramolecular bonds. Now what we're going to be looking at in this unit is interactions between molecules. Okay, there are 6 basic types of intermolecular forces that we're going to look at in Chapter 10. The first 3 listed here will be discussed in this presentation, and then there'll be a follow-up presentation dealing mostly with solids that will discuss the last 3. Okay, the first one we're going to look at are the dipole attractions, and this occurs in what we have referred to as polar molecules. Like here we see our electron cloud, and it has more positively charged side of the bond is at the hydrogen. The more negatively charged is the chlorine. And remember, when we're talking about positive and negative, we're talking about where the electrons are spending more of their time, or where they tend, the electron cloud has a higher probability density. So in this case, the chlorine has a higher electronegativity, and so we would expect that the probability density of the electrons is higher near the chlorine, because it attracts the electrons more strongly than the hydrogen does. Okay, so that hydrogen to chlorine bond that we were looking at above, that it would be our this right here, our intramolecular bond. Here, down here, we're seeing that if we have, in this case, 3 hydrogen chloride molecules, we have the positive hydrogen in one has an attraction for the negative chlorine in the other molecule, and that is what we're referring to as a dipole attraction, or a dipole intermolecular force. This is just to kind of give you a visual of these types of interactions. Okay, here's a picture out of the Zumdahl text, and here you can see an individual intermolecular force here, and then this is showing the B part of this figure is showing how if you have multiple molecules that they are going to kind of align themselves up, and the dipole interactions is what's going to determine the way that they align themselves. Okay, hydrogen bonds. Hydrogen bonds are a type of dipole attraction, and you have hydrogen that is bonded to an electron or an atom that has a high electronegativity, and we want to think here along the lines of fluorine, oxygen, and nitrogen. Okay, the reason that this forms such a strong dipole is two reasons, basically. One is the large difference in electronegativity between hydrogen and the oxygen, nitrogen, or fluorine, and then the other is the fact that because of the small size of the hydrogen and really of the nitrogen, oxygen, and fluorine, the molecules can get fairly close to each other, at least closer than they could with a larger atom involved. And so this makes for a particularly strong attraction. And so this picture here is showing you kind of what the hydrogen bonds look like from molecule to molecule. And so we see that because of the high electronegativity, the electrons tend to spend most of their time away from the hydrogen, which makes the hydrogen have more of a positive charge to it, and that positively charged hydrogen is going to be attracted to the negative electron cloud on the oxygen. If you remember, when we draw the Lewis structure of water, all right, and we have 2 lone pairs around the oxygen. Well, this is showing the lone pairs as these red ovals here. And so the positive hydrogen on one of these water molecules is attracted to the lone pair of electrons that's on the oxygen on an adjacent water molecule. And so that forms our hydrogen bond. So here's just another visualization. And one thing to notice about this is that the hydrogen bonding combined with the bond angle that we see in a water molecule makes for a very open crystalline structure when it forms a solid. Okay, so as it's cooling, these water molecules are going to align themselves up based on the hydrogen bonds, and that orientation gives the very open crystalline structure that makes solid water less dense than liquid water. So here again we see them lining up, and this would be similar to what you would see as the substance was cooling. The water molecules would orient themselves. Okay, London dispersion forces. Okay, these are relatively weak, and these are going to be the dominant intermolecular forces if we're talking about noble gases and also nonpolar molecules. Okay, now how does this form? Because so far we've been talking about the fact that we have something positive on one molecule that's attracted to something negative on the other molecule, and you're thinking, okay, well, we have neutral atoms, how's that going to happen? And have nonpolar molecules, which is supposed to have this nice equal sharing of the electrons, and so we don't have dipoles in those. Well, basically the way this works is that we have the creation of what they call an instantaneous dipole. And the way to think about this is, if you remember, when we talked about the electrons and electron clouds, we discussed the fact that the motion of the electrons is random. And as such, if you think about it, if their motion is totally random, then there is some probability, even if it's a small one, there is some probability that at a given time we would have a situation where, like we see here, let's see, in B, all right, like we see right here, where through just random movement we end up with, in this case, more electrons over on this side of our atom, and so we get this dipole that's created just through the random motion. Now, so what happens there? How does that? We know it's going to have this instantaneous dipole, but then random motion is also going to take the dipole away, basically. But the thing is that as soon as we get this instantaneous dipole, this atom, in this case we're calling it atom A, is able to induce a dipole in this adjacent atom B. So if you think about it, we have an instantaneous dipole formed, and so here, atom A, we have a more positive side here. Well, this is basically going to attract electrons and make the electrons in atom B more likely to be on the side that is attracted to the positive side of atom A. And so now we have this dipole formed and in adjacent molecules, or atoms in this case, and that is going to create what we are calling London dispersion forces. Now, if you think about it, it makes sense that there is some sort of intermolecular force at work when we're talking about these noble gases or nonpolar molecules, because if there weren't, then there would not be such a thing as a solid or liquid form of these substances. So there has to be some sort of intermolecular force at work.